On October 1st, 2025, two spacecraft orbiting Mars did something they were never designed to do. They turned away from the red planet entirely and pointed their cameras at a smudge in deep space, a visitor from beyond our solar system, 30 million kilometers away. Within weeks, the European Space Agency made a decision that shocked mission engineers: redirect a €1 billion Jupiter probe to chase this thing during the one window when Earth would be completely blind. No ground telescope could see it, only spacecraft already out there could watch. What did those Mars images show that triggered such an aggressive response? Stay with me until the end, because the answer might change how we think about what's drifting between the stars. Vor von Dios, Part 1, Opening Shot. Cold. Start. Mars observes the unexpected. Picture this. Somewhere in the cold silence of space, 30 million kilometers from Mars, a machine not built for this task turns its camera towards something it was never meant to see. The European Space Agency's Trace Gas Orbiter, designed to sniff methane in the Martian atmosphere and photograph canyon walls, suddenly pivots. Its instrument, Cassie's Color and Stereo Surface Imaging System, begins tracking a faint smudge against the starfield. This is Comet 3I Atlas, an interstellar visitor that entered our solar system from the cosmic void beyond. The images come back in stacks. Each exposure lasts 5 seconds. Engineers layer them, one atop another, teasing signal from noise. What emerges is ghostly, a fuzzy dot surrounded by a diffuse halo, the comet's coma glowing faintly as ice turns to gas under the distant sun's warmth. Stars streak across the frame in long trails because the spacecraft is tracking the comet's motion, following this stranger as it races through our neighborhood at speeds that betray its origin, somewhere out there, in the space between stars. Mars Express joins the effort. Between October 1st and 7th, 2025, both orbiters turn away from their primary mission to watch this thing pass. It's the closest any spacecraft has gotten to 3I Atlas so far. 30 million kilometers might sound like a lot, but in space terms it's practically intimate. The comet appears exactly as you'd expect, a nucleus hidden somewhere in that fuzzy glow, surrounded by a coma of gas and dust pushed outward by solar radiation and the comet's own internal pressure as frozen volatiles sublimate into space. But here's where it gets strange. Within weeks of these observations, the European Space Agency makes an announcement that almost nobody saw coming. JUICE, the Jupiter Icy Moons Explorer, a flagship mission worth over €1 billion, currently en route to the outer solar system, will be redirected. Not physically, not in terms of orbit, but in terms of attention. Between November 2nd and 25th, JUICE will turn its suite of cameras, spectrometers, and particle sensors toward 3I Atlas. It will observe this interstellar comet during a window when Earth-based telescopes will be blind, when the comet passes too close to the sun in our sky for ground observatories to track it without being overwhelmed by glare. Why? The official line is simple: opportunity. 3I Atlas is only the third confirmed interstellar object we've ever detected. The first, 1I/Oumuamua, streaked through in 2017 before anyone could organise a proper look. The second, 2I/Borisov, gave us a bit more time in 2019, but still, we were limited to Earth-based telescopes. Now, with 3I Atlas, we have spacecraft already out there, already in position. Why wouldn't we look? But the media reports started using words that ESA hadn't used: redirect, intercept, chase. Articles appeared suggesting that JUICE was being steered off course, that this was some kind of emergency maneuver, that perhaps ESA knew something they weren't saying. Forums lit up with speculation. Reddit threads multiplied. YouTube channels with names like Cosmic Secrets Revealed started pumping out videos with thumbnails showing the comet next to giant question marks. So let's be clear about what we're dealing with here. We have a comet, an icy, dusty body probably a few kilometers across, that came from outside our solar system. We have 2 Mars orbiters that took pictures of it. We have a Jupiter mission that will spend 3 weeks pointing instruments at it. And we have a growing sense, whispered in the comment sections and hinted at in the gaps between official statements, that maybe this is bigger than ESA is letting on. Is there something about this comet that triggered this decision? Did the Mars observations reveal something, an anomaly, a signature, a hint of something unexpected that made ESA's mission planners push for more aggressive action? Or is this exactly what it appears to be? A rare chance to study an interstellar visitor up close, taken simply because the opportunity exists. Here's what we know for certain. 3I Atlas was discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System in Hawaii. Its trajectory is hyperbolic, meaning it's moving too fast to be bound to our Sun. It came from somewhere else. It will leave and never return. And for a brief window in late 2025, we have machines positioned to watch it pass. What we don't know is whether those machines are merely watching, or whether they're searching for something specific, something that might justify the risk of diverting a billion-euro mission's attention away from its primary goals, even temporarily. Something that might explain why engineers who normally obsess over every percentage point of fuel margin and every degree of instrument pointing accuracy suddenly decided that a comet nobody had heard of 4 months ago was worth the trouble. The question isn't just what ESA is doing. The question is, what did they see that made them decide to do it? And why now, when the comet is about to pass through the one part of its trajectory where Earth can't watch, when only spacecraft already in deep space can keep eyes on this thing as it rounds the Sun and begins its journey back out into the dark? We're going to find out. But first, we need to understand what ESA is actually saying versus what everyone else is hearing. Shussaka 1 Hor. Part 2. Official ESA Statement versus Leaks and Interpretations. Wall. The European Space Agency's official statement is, frankly, pretty boring. Between October 1st and 7th, the Trace Gas Orbiter and Mars Express conducted observations of Comet 3I Atlas as it passed within reasonable observing distance of Mars. They used their imaging systems, particularly TGO's CAS's camera, to capture stacked exposures of the comet. The purpose? Scientific opportunity. The result? Images showing a faint cometary coma and tail. Mission accomplished. As for JUICE, the statement is similarly measured. The spacecraft will observe 3I Atlas between November 2nd and 25th, using its optical cameras, infrared and ultraviolet spectrometers, and particle environment sensors. The observations will take advantage of JUICE's position in space during this period, when the comet will be difficult to observe from Earth due to solar conjunction, meaning it will appear too close to the Sun in our sky. JUICE, travelling through interplanetary space on its way to Jupiter, faces no such constraint. Notice what the statement doesn't say. It doesn't say redirect. It doesn't say intercept. It doesn't say emergency maneuver or unprecedented response or secret mission. It says, we're going to point some instruments at an interesting object because we can. But that's not the story that spread. Within days of the announcement, headlines started appearing that told a different tale. Jupiter mission diverted to intercept interstellar comet. ESA steers billion-dollar spacecraft toward mysterious visitor. One article from IFL Science described the decision as unexpected for everybody, implying a sudden, reactive choice rather than a planned observation campaign. Forums buzzed with speculation about delta V burns, changes to JUICE's actual trajectory, and whether the spacecraft was being pushed off its carefully calculated path to Jupiter. Here's where it gets murky. Some of this is simple confusion about terminology. In spaceflight, redirect can mean physically changing course, which requires fuel and alters your trajectory. Or it can mean simply reorienting, turning the spacecraft to point instruments in a different direction without actually changing where it's going. JUICE is doing the latter. Its trajectory toward Jupiter remains unchanged. What's changing is where its cameras and sensors are looking during a specific 3-week window. But some of the speculation isn't confusion, it's interpretation. Mission engineers and scientists who work on these programs don't always speak to the media, but they talk to each other. They post in professional channels, they attend conferences, they share observations over email chains, and sometimes those communications leak outward in diluted form. A comment here about tight margins, a mention there about non-standard pointing, a phrase like thermal constraints in the inner system. One engineer, speaking off the record to a space news site, supposedly said that the JUICE observations were pushed through faster than normal approval channels, suggesting that this wasn't in the original mission timeline. Another source mentioned that some team members raised concerns about instrument safety, particularly regarding stray, Light contamination and thermal loads when pointing instruments sunward in the inner solar system, where JUICE wasn't designed to operate extensively. Are these leaks real? Are they exaggerated? Are they being taken out of context? It's hard to say. ESA hasn't confirmed any internal debate. Officially, everything is proceeding nominally. The observations are characterized as a bonus science opportunity, not a risky deviation. But here's the thing about space missions. They are planned down to the second. Every action is scripted months or years in advance. Pointing budgets, fuel margins, data downlink schedules, all meticulously calculated. Adding an unplanned 3-week observation campaign isn't like deciding to take a detour on a road trip. It's more like deciding to repaint your house while you're in the middle of moving across the country. Possible? Yes. Trivial? No. So why the discrepancy between ESA's calm, matter-of-fact tone and the swirl of speculation? Part of it is the nature of media amplification. A measured statement gets transformed as it passes through news cycles. JUICE will observe becomes JUICE redirected becomes JUICE chasing comet. Each iteration adds a layer of drama that wasn't in the original, but part of it might be something else. Maybe there's a gap between what ESA is willing to say publicly and what's being discussed internally. Maybe mission planners are genuinely excited or concerned about something they saw in the Mars observations. Maybe the decision to observe 3i Atlas with JUICE was more contentious than the public statements let on. Maybe there's a split between those who see this as a golden opportunity and those who see it as an unnecessary risk. Consider the timeline. Atlas discovers the comet on July 1st. By early October, Mars orbiters are imaging it. By mid-October, ESA announces JUICE observations for November. That's fast. Mission timelines usually involve committees, review boards, technical assessments, risk analyses. To greenlight a multi-week observation campaign in a matter of weeks suggests either exceptional efficiency or exceptional motivation. What could motivate that kind of speed? Perhaps the Mars images showed something, an unexpected brightness variation, an asymmetric coma structure, an outgassing pattern that didn't match models. Perhaps ground-based telescopes contributed data that raised eyebrows. Perhaps someone high up in ESA's science directorate looked at the preliminary results and said, "We need more. We need JUICE on this." Or perhaps it's simpler. Perhaps this is exactly what ESA claims, a rare alignment of opportunity and capability. An interstellar comet passing through at a time when we happen to have a spacecraft positioned to observe it during a critical window. A chance to gather data that would otherwise be lost forever. No conspiracy, no hidden agenda, just science responding to opportunity. But if that's the case, why the whispers? Why the unnamed? Sources? Why the sense, reading between the lines of technical papers and mission updates, that there's more going on beneath the surface? The answer might lie in what happens next. November 2nd to 25th is the window. During those 3 weeks, 3i Atlas will be in a part of its orbit where Earth-based telescopes are hamstrung by geometry and glare. JUICE will have the sky to itself. What it sees or doesn't see will either vindicate ESA's decision or raise even more questions. And to understand why November matters so much, we need to talk about trajectories, timing, and the narrow windows that govern everything in space. Jagwonjkian, Part 3. Trajectory, Timing and Windows. Why November Matters. Jagwondan, Comet 3i Atlas, didn't just wander into our solar system on a lazy afternoon. It came screaming in from interstellar space on a hyperbolic trajectory, a path shaped like an open curve, not a closed ellipse. This means it's not bound to our sun. It's not one of ours. It came from somewhere else, fell toward our star due to gravity, swung around, and will leave forever. The closest it gets to the Sun, perihelion, occurs on October the 29th, 2025, at a distance of roughly 1.36 to 1.4 astronomical units. That's just inside Mars's orbit, farther out than Earth, but closer than Jupiter. After perihelion, the comet's trajectory carries it outward again. On November 3rd, it passes near Venus, not close enough to hit, but close enough that Venus-based hypothetical observers would get a decent view. Then it continues outward, crossing Earth's orbit, heading toward the outer system. By March 2026, it will pass near Jupiter, though near in this context still means millions of kilometers away. After that, it's gone. Back into the interstellar medium, back into the space between stars where it will drift for millions or billions of years until maybe, just maybe, it falls toward another star system entirely. But here's the problem with observing 3I Atlas from Earth during its closest approach. Around perihelion, late October into early November, the comet appears very close to the Sun in our sky. Not physically close to the Sun, but close from our perspective. This creates what astronomers call solar conjunction. Try to point a telescope at something near the Sun and you're asking for trouble. Stray sunlight floods your sensors. Thermal loads spike. You risk damaging delicate instruments. Ground-based observatories can't observe objects within a certain angular distance from the Sun, typically around 30 degrees, depending on the telescope and atmospheric conditions. So right when 3I Atlas is closest to the Sun, most active, most interesting, when its ices are sublimating fastest, when its coma is brightest, when outgassing jets are most dynamic, Earth-based telescopes are essentially blind. We lose the best part of the show to geometry, unless you have a spacecraft that doesn't care about Earth's position relative to the Sun. JUICE, travelling through interplanetary space, doesn't have that constraint. Its position relative to the comet and the Sun is completely different from Earth's. During November, JUICE can observe 3I Atlas at angles and under conditions that ground telescopes simply cannot match. This is why the window matters. This is why ESA scheduled observations for November 2nd to 25th. It's not arbitrary. It's the period when JUICE has something no one else has, line of sight. But it's not without trade-offs. JUICE wasn't designed to operate extensively in the inner solar system. It's built for the outer system, cold, distant, far from the Sun. As it swings through the inner system on its complex trajectory toward Jupiter, a path that includes multiple flybys of Earth and Venus for gravitational assists, it enters environments it wasn't optimized for. Closer to the Sun means higher solar flux, more heat, more intense radiation. Instruments designed for the dim, frigid environment around Jupiter's moons suddenly have to contend with thermal loads they weren't primarily designed to handle. Engineers build in margins for this, of course. JUICE's designers knew it would pass through the inner system during its cruise phase. They included thermal shielding, they planned power and cooling budgets, they tested instruments under a range of conditions. But there's a difference between passing through and loitering, spending 3 weeks pointing instruments at a target in the inner system, collecting data, adjusting pointing, managing thermal loads. That's not nominal, that's pushing boundaries. There are also constraints on pointing. Spacecraft have keep-out zones, directions they're not supposed to point their instruments, because doing so would expose sensitive components to sunlight or heat. Pointing at 3I Atlas during November might require careful choreography to avoid these zones, which limits observation windows and viewing angles. It might require turning off certain instruments or subsystems to manage power and heat. It might require more frequent attitude adjustments, which burns fuel and wears out reaction wheels. The spinning masses that help orient the spacecraft without using thrusters. All of this eats into margins: fuel margin, thermal margin, mechanical margin, data downlink margin. Every mission has reserves built in for contingencies, but you don't want to drain them unless you have good reason. JUICE still has years to go before it reaches Jupiter. It still has multiple complex flybys ahead, intricate orbital maneuvers, and eventually the high-stakes insertion into the Jovian system. You don't gamble with those margins lightly. So the question becomes, is observing 3I Atlas worth the cost? ESA apparently thinks so, but what makes this particular comet compelling enough to justify the risk? Part of the answer might lie in what the Mars observations revealed. Remember, TGO and Mars Express got the closest look anyone's had at 3I Atlas so far. 30 million kilometers is still far, about 80 times the distance from Earth to the Moon, but in terms of spacecraft observations of comets, it's respectable, and stacking multiple exposures allowed them to pull out details that might have been invisible in single frames. What did they see? Officially, a coma and tail, a fuzzy blob, as expected. But unofficially, that's where things get interesting. Some reports mentioned asymmetry in the coma brightness distribution. Not a perfectly spherical halo, but something lopsided suggesting directional outgassing, jets of gas and dust erupting from specific regions of the nucleus. This is common in comets, but the pattern and intensity can tell you things about the nucleus's composition, structure, and rotation. There were also hints, unconfirmed, speculative, of larger-than-expected dust particles resisting solar radiation pressure. Normally sunlight pushes on dust, creating a tail that points away from the sun. Smaller particles get pushed harder, larger particles less so. If the dust is heavier or stickier than expected, it suggests something about the ice composition, or the way material is being ejected from the nucleus. Maybe the comet has more complex organics. Maybe its ices are mixed with minerals in unusual ways. Maybe there's internal pressure, pockets of gas building up beneath the surface and bursting out explosively. These are subtle clues, the kind that make scientists sit up and say, "Huh, that's odd." And when something's odd, you want more data, better data. Data from different angles, different instruments, different wavelengths. Enter JUICE. Its instrument suite includes optical cameras, infrared spectrometers to analyze chemical composition, ultraviolet sensors to detect gases like water vapor and carbon dioxide, magnetometers and particle detectors to study the comet's interaction with the solar wind. Point all of that at 3i Atlas for 3 weeks, and you get a dataset unlike any previous interstellar comet observation. But you also take a risk, you commit resources, you accept trade-offs, and you do it during a window when nobody else can see what you're seeing. If something goes wrong, if an instrument glitches, if thermal loads exceed safe limits, if a pointing error causes the spacecraft to enter safe mode, there's no backup. No ground telescopes to fill in the gaps, just JUICE, alone in space, trying to capture data on a comet that will never come back. That's why November matters. It's the moment when we're blind from Earth, when the comet is in the solar glare, when only a spacecraft already positioned in deep space can keep watch. It's a window of opportunity, yes, but it's also a window of vulnerability. What JUICE sees, or fails to see, will define our understanding of 3i Atlas. And perhaps, just perhaps, it will reveal why ESA was willing to push boundaries to make this happen. So what did the Mars footage actually show? Let's dig into the images themselves and see if we can find the clues that might have triggered this whole sequence of events. Part 4. What the Mars footage showed, or implied, when the Trace Gas Orbiter and Mars Express turned their cameras toward 3i Atlas, they weren't using instruments designed for deep space imaging. CASIS, the Colour and Stereo Surface Imaging System, was built to photograph Mars. Cliffs, craters, dust storms, polar ice caps, not comets 30 million kilometers away. But space missions are adaptable. Engineers love a challenge, so they tried something clever. They used a technique called stacking. Take multiple short exposures, each lasting about 5 seconds, and layer them on top of each other. Each individual frame is noisy, grainy, barely showing anything, but stack dozens of them together, aligning the comet's position in each frame, and the random noise averages out while the comet's signal adds up. What emerges is something you can actually see, a faint, fuzzy dot surrounded by a diffuse glow. That glow is the coma, the cloud of gas and dust surrounding the nucleus. As the comet approaches the sun, solar heat warms the surface. Ices, water, carbon dioxide, carbon monoxide, methane sublimate directly from solid to gas. The gas expands outward, carrying dust particles with it. Solar radiation and the solar wind push on this material, creating the tail. From Earth, comets can appear spectacular, long sweeping tails arcing across the sky. From 30 million kilometers away, through a camera not built for this, 3i Atlas looks like a smudge. But it's a scientifically interesting smudge. The images show several things. First, the coma is there, and it's active. This confirms that 3i Atlas is indeed a comet, not some inert rock, or, despite the wilder internet theories, an engineered probe. It's outgassing. It's behaving exactly as you'd expect an icy body to behave when heated by the sun. Second, the coma isn't perfectly symmetrical. There's a brightness gradient, subtle but detectable. One side appears slightly more luminous than the other. This suggests that outgassing isn't uniform across the nucleus. Maybe the nucleus is rotating, and different regions have different compositions. Maybe there's a large active area, a jet source, on one side. Maybe the nucleus itself is irregularly shaped, creating uneven heating. Third, there's structure in the coma. Not just a smooth blob, but variations in brightness, hints of arcs or filaments. These could be dust streams, material ejected at different times from different locations on the nucleus, each following slightly different trajectories through space. Or they could be optical effects, artifacts of the stacking process. It's hard to say from images alone. But here's where it gets interesting. The Mars observations didn't happen in isolation. Around the same time, other telescopes were watching too. The James Webb Space Telescope, humanity's most powerful infrared observatory, turned its gaze toward 3I Atlas. JWST doesn't just take pictures, it takes spectra, detailed analyses of light broken down by wavelength, revealing the chemical fingerprints of whatever's out there. JWST's observations revealed something surprising. 3I Atlas has an unusually high ratio of carbon dioxide to water. Most comets are dominated by water ice. When they outgas, water vapor is the main component, with carbon dioxide, carbon monoxide, and other species as minor players. But 3I Atlas flips the script. Its CO, 2 to H2O ratio is around 8 to 1. For every molecule of water, there are 8 molecules of carbon dioxide. This is weird. It's not unheard of, some comets show elevated CO2, but it's unusual. It suggests that 3I Atlas formed in a cold environment where carbon dioxide could condense as easily as water, or perhaps where water was less abundant. It suggests a formation region different from most solar system comets, which makes sense given that this thing came from outside our system. Different star, different protoplanetary disk, different chemistry. Ground-based telescopes added more pieces to the puzzle. Gemini Observatory and NASA's Infrared Telescope facility detected water ice in the coma, not just water vapor, but actual ice particles mixed in with the gas. They also noted that the comet's color, its optical spectrum, is unusually red. Redder than most comets, more like certain types of asteroids. This redness could come from organic compounds, complex carbon-based molecules that form in cold, radiation-rich environments. Think tholins, the stuff that gives Pluto its reddish hue. Ultraviolet observations detected hydroxyl, OH, emission at large distances, out beyond 3 astronomical units. Hydroxyl is a fragment of water molecules broken apart by sunlight. Its presence means water was active even when the comet was far from the sun, colder than you'd normally expect for vigorous outgassing. This suggests either a very volatile rich surface or some internal heat source driving activity. And then there's the polarimetry. Scientists measured how light scattered off the comet's dust particles becomes polarized, oscillating in preferred directions rather than randomly. The polarization curve for 3I Atlas is bizarre. It shows extreme negative polarization, reaching around negative 2.7% at a phase angle of 7 degrees with an inversion angle, the point where polarization switches from negative to positive, around 17 degrees. This curve shape is unlike anything seen in solar system comets. What does that mean? Polarization tells you about the size, shape, and composition of dust particles. Extreme negative polarization suggests very small particles, possibly fluffy aggregates, possibly coated with organics, possibly structured in ways that scatter light, differently than typical comet dust. It's a signature, a fingerprint. And 3I Atlas's fingerprint doesn't match the usual suspects. Put all of this together, asymmetric outgassing, high CO2 to water ratio, red coloration, unusual dust properties, active at large distances. Each observation alone might be interesting but not alarming. Together they paint a picture of something genuinely odd. Not alien, there's no evidence of anything non-natural, but anomalous, different enough to demand attention. Could this be what triggered ESA's decision to commit JUICE? Imagine the scene. Mission scientists reviewing the Mars orbiter data, cross-referencing with JWST spectra, reading reports from ground telescopes. Someone notices the patterns. Someone says, "This doesn't look like 2I/Borisov. This doesn't look like most comets. We need more data." Someone else points out that JUICE will be in position during November, during the solar conjunction window when Earth can't watch. Someone makes the call, let's do it. Or maybe it's more prosaic. Maybe ESA simply saw an opportunity and took it. Maybe there's no hidden mystery, just solid science. But the anomalies are real. The strangeness is documented. And whether ESA is responding to something specific or just seizing a rare chance, the fact remains. They're committing significant resources to observe this particular comet during a narrow window when they'll be the only ones watching. What we don't know yet is whether those observations will explain the anomalies or deepen them. Whether JUICE will return data that makes 3I Atlas fit neatly into our models of interstellar comets, or whether it will hand us more puzzles to solve. But before we can understand what JUICE might find, we need to understand how the scientific community reacted to all of this. Because not everyone was thrilled. Not everyone thought this was a good idea. And some of the dissent reveals just how controversial and how risky this decision might actually be. Ya Dios. Part 5. Immediate reactions, controversy and dissent. The announcement that JUICE would observe 3I Atlas landed in the space science community like a stone in a pond. Ripples spread outward. Some were ripples of excitement, others were ripples of concern, a few were ripples of outright skepticism. On one hand, you had the enthusiasts. Planetary scientists who study comets saw this as a golden opportunity. Interstellar objects are rare. We've confirmed exactly 3. 1I/Oumuamua, 2I/Borisov, and now 3I Atlas. Each one teaches us something about the diversity of planetary systems beyond our own, about the materials and processes that exist elsewhere in the galaxy. Getting spacecraft data on one of these objects is invaluable. Ground telescopes are great, but nothing beats being there, or at least having a machine there, measuring composition, dust properties, particle environment, all in real time. Articles appeared, celebrating the decision. Space.com ran a piece highlighting how Mars and Jupiter probes would team up to study the comet. Planetary Society bloggers wrote about the science returns, speculating on what JUICE's instruments might reveal. Social media lit up with space enthusiasts sharing images, diagrams of the comet's trajectory, speculation about what we'd learn. But alongside the excitement, there was noise, the kind of noise that always accompanies anything unusual in space. YouTube channels with dubious credentials started posting videos suggesting that 3I Atlas might be an alien probe, that its unusual properties, high CO2, strange dust, red coloration, could indicate artificial construction, that ESA's decision to observe it so aggressively was driven by classified intelligence, secret signals, evidence of non-natural origin. This is nonsense, of course. NASA scientists and ESA researchers publicly addressed these claims, patiently explaining that everything observed about 3I Atlas is consistent with natural cometary behavior. Hyperbolic trajectories are expected for interstellar objects. They're not bound to the Sun, so of course they move fast. Outgassing is normal for comets. CO2-rich comets exist in our own system. 3I Atlas just happens to be more extreme. The polarimetry, the dust, the colour, all of it points to a comet that formed under different conditions than solar system comets, which is exactly what you'd expect for an object from another star system. The Guardian ran an article specifically debunking the alien theories, quoting astronomers who emphasised that there's zero evidence for anything non-natural. The comet behaves like a comet. It looks like a comet. It is a comet. But here's the thing about debunking. It doesn't always work. For every careful explanation, there's a comment section filled with, "But what if?" and "They would say that. And why are they really observing it then?" Conspiracy thinking thrives on ambiguity. And ESA's measured, cautious public statements, necessary for a responsible space agency, leave just enough ambiguity for imaginations to run wild. Setting aside the fringe theories, though, there was legitimate concern within the mission community. Not about aliens, about resources. JUICE is a flagship mission. It cost over €1 billion. It launched in April 2023 and won't reach Jupiter until July 2031. That's an 8-year cruise, most of it spent in the inner solar system executing a complex series of gravity-assist flybys, Earth, Venus, Earth again, Earth a third time, to build up the velocity needed to reach Jupiter. Every maneuver is planned to within meters per second. Every instrument operation is scheduled to maximize science return while preserving spacecraft health. Adding an unplanned 3-week observation campaign means diverting attention and resources. It means adjusting pointing schedules, managing thermal loads, allocating data downlink bandwidth, consuming fuel for attitude adjustments. And it means doing all of this during a phase of the mission when the spacecraft is in the inner system, closer to the Sun than ideal, operating outside its comfort zone. Some mission scientists voiced caution. Not publicly, space agencies don't usually air internal debates, but in professional circles, in conference hallways, in email threads. Concerns about thermal margins, concerns about reaction wheel wear, concerns about whether this might set a precedent for future requests to divert flagship missions toward targets of opportunity, eroding the focused science programs they were designed to execute. There's also a philosophical tension. JUICE's primary mission is to study Jupiter's icy moons, Ganymede, Callisto, Europa. These are worlds with subsurface oceans, potential habitats for life, key targets in astrobiology. The mission was selected, funded, and built specifically for this purpose. Spending time and resources on a comet, no matter how interesting, could be seen as mission creep, a distraction from the core goals. On the other hand, flexibility is valuable. Missions that can respond to unexpected opportunities often produce groundbreaking science. Voyager's encounter with Jupiter's moon Io revealed active volcanoes, something nobody expected. Cassini's discovery of geysers on Enceladus happened because the mission team was willing to adjust plans and take a closer look. If you're too rigid, you miss serendipity. So where does that leave us? ESA decided the science return justified the cost. They calculated the risks, thermal, fuel, pointing, data, and concluded they were acceptable. They scheduled the observations for a window when JUICE is uniquely positioned to gather data nobody else can get. And they're proceeding. But the decision wasn't without controversy. And the stakes are real. If JUICE's observations succeed, if the data returned is rich and revealing, then ESA's gamble will be vindicated. They'll have demonstrated agility, responsiveness, and scientific courage. They'll have captured data on an interstellar comet that would otherwise have been lost. If something goes wrong, if an instrument fault occurs, if thermal loads exceed safe limits, if a pointing error forces the spacecraft into safe mode, then ESA will face difficult questions. Was it worth the risk? Did they jeopardize €1 billion mission for marginal returns? Did they prioritize headlines over mission integrity? We won't know the answer until after November 25th, when the observation campaign ends and the data starts flowing back. Until then, we're left with anticipation, speculation, and the knowledge that somewhere out there, a spacecraft is preparing to turn its instruments toward a visitor from beyond our solar system during the one window when Earth can't watch. And that brings us to the deeper questions. Not just what ESA is doing, but how they're doing it. What are the engineering constraints? What are the margins they're working with? How much fuel, pointing capacity, and operational flexibility does JUICE actually have? Let's pull back the curtain and look at the machinery behind the mission. First, Part 6. Fuel, Delta V and Orbital. Attitude margins. Jurosti. Spacecraft are fragile, expensive machines operating in an unforgiving environment. Every action costs something. Every pointing maneuver, every instrument activation, every adjustment to the trajectory, it all draws from finite reserves. Fuel, power, data bandwidth, thermal capacity. You launch with what you have and you can't refill. So mission planners obsess over margins, the buffer between what you need and what you have, the cushion that keeps you alive when something unexpected happens. For JUICE, those margins are calculated across an 8-year cruise and a 4-year science mission at Jupiter. The spacecraft carries roughly 600 kilograms of chemical propellant for its main engine and bipropellant thrusters. This fuel is used for trajectory correction maneuvers, orbital insertion at Jupiter, and major burns. It also carries about 54 kilograms of cold gas and nitrogen for fine attitude control via smaller thrusters. Every time JUICE adjusts its orientation, every time it points instruments in a new direction, it either uses reaction wheels, spinning masses that exchange angular momentum, or it fires thrusters. Reaction wheels are preferred because they don't consume propellant, but they have limits. They can only spin so fast before they saturate. When that happens, you need to desaturate them by firing thrusters to dump angular momentum. That uses fuel. Now, pointing instruments at 3i Atlas doesn't change JUICE's trajectory. The spacecraft isn't burning fuel to chase the comet or alter its path to Jupiter, but it is reorienting. Normally during cruise, JUICE maintains a relatively stable attitude, pointing its solar panels toward the sun for power and its high-gain antenna toward Earth for communication. To observe the comet, it needs to slew, rotate its entire body, so that cameras and spectrometers point at 3i Atlas. This requires momentum management. Spin up reaction wheels, rotate the spacecraft, hold the new attitude, track the comet as it moves relative to JUICE's position, adjust for drift, then slew back to nominal attitude afterward. Each slew, each tracking adjustment, Each desaturation maneuver uses a little fuel. Not much individually, we're talking grams or tens of grams per event, but it adds up. Over 3 weeks of observations with multiple pointing adjustments per day, you could consume a kilogram or more of cold gas. Maybe more if thermal constraints force you to rotate away from the sun periodically to cool sensitive instruments, then rotate back. A kilogram doesn't sound like much against 54 kilograms total, but remember, margins. That fuel wasn't sitting there unallocated, it was budgeted. For contingencies, unexpected attitude disturbances, safe mode recoveries, extended mission scenarios. Now you're pulling from that reserve. If you use 5% of your cold gas margin on comet observations, and later encounter a problem that requires aggressive attitude control, a stuck reaction wheel, a software glitch, a collision avoidance maneuver, you might not have enough buffer. Thermal margins are another concern. JUICE was designed for the cold outer solar system, where the sun is dim and heat dissipation is easy. As the spacecraft swings through the inner system during its cruise phase, solar intensity increases dramatically. At Earth's orbit, solar flux is about 1,368 watts per square meter. At Mars orbit during JUICE's encounter, it's still around 500 to 600 watts per square meter. That's manageable with proper orientation, keep solar panels edge onto the sun, use thermal blankets, radiate excess heat into space. But when you start pointing instruments sunward, or toward targets that require non-optimal thermal attitudes, things get tricky. Cameras and spectrometers have operating temperature ranges. Too hot and sensors generate noise, electronics malfunction, optical elements degrade. JUICE's instruments include protective covers, baffles to block stray light, and thermal control systems. But these systems were optimized for Jupiter, where the sun is faint and distant. Using them aggressively in the inner system pushes boundaries. Engineers model this, of course. They simulate worst-case thermal loads. They calculate safe pointing zones, areas of the sky where instruments can look without exceeding temperature limits. But models have uncertainties. Real-world conditions sometimes surprise you. A reflective surface you didn't account for bounces extra sunlight onto a sensor. A thermal blanket degrades slightly over time, reducing effectiveness. A software error causes an instrument to stay active longer than planned, generating extra heat. If JUICE's thermal margins are tight during the November observation window, mission operators might need to limit exposure times, restrict certain instrument modes, or periodically rotate the spacecraft to cool down. All of that affects data quality and quantity. You're making trade-offs. More observation time means more thermal risk. Less observation time means less data. Where do you draw the line? Then there's data downlink. JUICE communicates with Earth via its high-gain antenna, transmitting science data back to ground stations. Bandwidth is limited by distance. The farther you are, the weaker the signal, and by pointing constraints. You can't transmit data while you're pointing instruments at a comet, unless the antenna happens to point Earthward at the same time, which is unlikely. So observations and communication happen in shifts. Observe, store data on board, slew to Earth pointing attitude, downlink, slew back, observe more. The spacecraft's onboard solid-state recorder has finite capacity. If you're generating data faster than you can downlink it, lots of images, spectra, particle measurements, you risk filling up storage. When storage is full, you either stop collecting data or start overwriting old data. Mission planners have to balance observation intensity against downlink opportunities. And remember, ESA's deep space network has limited time available. Ground stations serve multiple missions. JUICE gets allocated slots, but those slots are scheduled months in advance. Adding extra downlink passes for comet data might mean bumping other activities or accepting delays in returning the data to Earth. There's also pointing accuracy. Tracking a comet requires knowing where it is relative to the spacecraft. 3i Atlas is moving on a hyperbolic trajectory at tens of kilometers per second. JUICE is moving on its own trajectory at a different velocity. Calculating the relative positions requires precise knowledge of both orbits, which requires tracking data from ground telescopes and spacecraft navigation measurements. Any uncertainty in the comet's position translates to pointing error. Point slightly wrong and your camera captures empty space instead of the comet. Point very wrong and you waste a whole observation sequence. To mitigate this, operators likely use onboard star trackers to confirm pointing. The spacecraft knows where it's pointing relative to background stars. Ground teams provide predicted coordinates for the comet. Software adjusts pointing in real time based on star tracker data and stored comet ephemeris. But this requires additional computation, additional attitude adjustments, additional fuel expenditure for fine-tuning. All of these factors, fuel, thermal, data, pointing, interact. A decision to extend an observation by 10 minutes might seem minor, but it could trigger a cascade. 10 more minutes of observation means 10 more minutes of non-nominal thermal attitude, which might push a sensor closer to its temperature limit. That might require a cool-down maneuver which uses fuel. The extra data might require an additional downlink pass, which competes with other mission activities. The extended attitude hold might saturate a reaction wheel faster, requiring earlier desaturation, which uses more fuel. This is the complexity of deep space operations. Everything connects. Margins matter, because when they're gone, you're operating without a safety net. ESA's engineers calculated that observing 3I Atlas fits within acceptable risk. They determined that the fuel cost, thermal load, data bandwidth, and pointing demands were manageable. But manageable doesn't mean trivial. It means they're accepting some risk, consuming some margin, betting that the science return justifies the cost. What we don't know, what ESA hasn't publicly detailed, is exactly how tight those margins are. How much buffer remains after the comet observations? How close to limits are they operating? If something unexpected happened, a software glitch, a hardware fault, an unplanned attitude disturbance, how much reserve is left to handle it? These aren't idle questions. Deep space missions have failed or been compromised by margin erosion. Lost fuel reserves, degraded instruments, accumulated wear on mechanical systems. Every mission walks a tightrope between ambition and caution. JUICE is ambitious. This comet observation adds to that ambition. Whether it tips the balance from bold to reckless depends on details we don't have access to. But here's the thing. If ESA were truly worried, they wouldn't do it. Space agencies are conservative by necessity. Failures are public, expensive, and career-ending. The fact that they greenlit this campaign suggests they're confident the margins hold, or at least confident enough to take the bet. Which brings us to a more provocative question. What if they're not just observing? What if there's more to this than pointing instruments from afar? What if someone, somewhere within ESA, has considered something more aggressive? A real intercept, a flyby, a close approach? Is that even possible? Let's explore the physics and see how far the rabbit hole goes. Just wondrous. Part 7. The intercept. Hypothesis, could ESA push further? Just wondrous. Let's be clear from the start. There's no public evidence that ESA is planning a physical intercept of 3I Atlas. The official plan is remote observation, pointing instruments at the comet from JUICE's current trajectory, millions of kilometers away. But the internet doesn't traffic in official plans. It traffics in speculation, possibility, and the tantalizing what if. So let's entertain the idea. Could JUICE actually fly by 3I Atlas? What would that take? First, understand what an intercept means. It's not just pointing a camera. It's altering your trajectory so that your path crosses the comet's path in space and time. You need to be at the same place at the same moment, moving along a trajectory that brings you within a target distance, maybe hundreds of kilometers, maybe thousands, depending on your instrument's capabilities and your risk tolerance. JUICE's current trajectory is a carefully choreographed dance through the inner solar system, using gravity assist from Earth and Venus to build up velocity for the eventual journey to Jupiter. The spacecraft is on a precisely calculated path. Deviating from that path requires delta V, change in velocity, and delta V costs fuel. How much fuel? That depends on how big a deviation you need. Let's think about the geometry. 3I Atlas is on a hyperbolic trajectory passing through the inner solar system. JUICE is on its own complex path. At any given time, the two objects are separated by millions of kilometers, moving in different directions at different speeds. To intercept, you'd need to calculate a trajectory that brings JUICE from its current position to a point along the comet's path at the right time. This is called a Lambert problem in orbital mechanics, finding the trajectory that connects two points in space given a travel time. The solution gives you the required delta V. For a rough estimate, if JUICE and 3I Atlas are separated by say 50 million kilometers and moving with relative velocity of tens of kilometers per second, You'd need multiple kilometers per second of delta V to achieve intercept. That's enormous. JUICE's total delta V budget, the maximum velocity change its fuel can provide, is somewhere around 2 to 3 kilometers per second for its entire mission. You can't spend that on a comet intercept. You'd have nothing left for Jupiter orbit insertion, which is the whole point of the mission. So a true intercept, bringing JUICE within close flyby distance of 3I Atlas, is almost certainly off the table. The fuel cost is prohibitive. It would require sacrificing the Jupiter mission entirely. But what about a less extreme scenario? What if you didn't aim for a close flyby, but instead adjusted your trajectory slightly to bring you closer than you'd otherwise be? Not hundreds of kilometers, but maybe 10 million instead of 50 million? A much smaller delta V, possibly achievable with tens or low hundreds of meters per second. That's within the realm of a possible trajectory correction maneuver. Here's where it gets interesting. JUICE has already performed multiple trajectory correction maneuvers during its cruise phase. Small burns to refine its path, correct for navigation errors, set up gravity assists. These are expected and budgeted. If you embedded an additional small burn ostensibly for trajectory correction, but actually designed to bring you closer to 3I Atlas's path, you could potentially shave some distance off without raising alarms. Is this plausible? Technically, yes. Politically and operationally, probably not. Trajectory changes are scrutinized by mission teams, navigation experts, and oversight committees. You can't just sneak in a burn without justification, and even a small detour risks perturbing your carefully planned gravity assists. Miss your Earth flyby target by a few hundred kilometers, and your whole trajectory to Jupiter shifts. That's unacceptable. There's also the timing problem. To intercept 3I Atlas at a specific point, you need to adjust your trajectory well in advance. Orbital mechanics doesn't allow for last-minute swerves. The earlier you burn, the less fuel you need to achieve a given position change, but also the more uncertainty accumulates. The later you burn, the more fuel required. There's an optimal window, and that window has likely already passed for any meaningful intercept during November 2025. Some observers have speculated about Juno, NASA's Jupiter-orbiting spacecraft, potentially intercepting 3I Atlas when the comet passes near Jupiter in March 2026. Juno is already at Jupiter, orbiting the planet in a highly elliptical path. Could it adjust its orbit to fly by the comet? Theoretically, if the geometry were favourable and Juno had sufficient fuel, yes, but Juno's fuel reserves are limited. It's been at Jupiter since 2016, executing an extended mission well beyond its original timeline. Every remaining drop of fuel is precious. Diverting Juno for a comet flyby would likely compromise its ongoing science at Jupiter, and NASA would need to weigh that trade-off carefully. The same logic applies to JUICE. Even if a small trajectory adjustment were possible, even if the fuel cost were acceptable, the risk might not be. Deep space navigation is precise but not perfect. Comets outgas, ejecting material that exerts tiny forces on the nucleus, altering its trajectory in unpredictable ways. This non-gravitational force makes comets harder to track than asteroids. If you're planning a flyby and the comet's position shifts unexpectedly, you could miss your target entirely. Or worse, fly through a dense region of dust and gas, risking impacts that could damage solar panels, instruments, or critical systems. Space agencies are risk-averse when it comes to flagship missions. €1 billion spacecraft is not something you fly through a comet's coma on a whim. The potential science return would need to be extraordinary to justify that kind of danger. And so far, there's no indication that 3I Atlas presents such an extraordinary opportunity. So where does that leave the intercept hypothesis? Probably in the realm of fan fiction. Fun to think about, interesting as a thought experiment, but not something ESA is actually doing. The official observation campaign, remote sensing from millions of kilometers away, is ambitious enough. It stretches margins, consumes resources, and tests operational boundaries. Adding a physical intercept on top of that would cross from bold into reckless. That said, the fact that people are speculating about it tells you something. It tells you that 3I Atlas has captured imaginations in a way that most comets don't. It tells you that there's a hunger for more aggressive exploration, a desire to push boundaries, to do more than just watch from afar. And it tells you that when a space agency makes an unusual decision, like redirecting a flagship mission to observe an interstellar comet, people notice. They ask questions. They wonder what else might be possible. Maybe ESA is simply doing good science, seizing an opportunity that won't come again. Or maybe, just maybe, there are motivations beyond pure science. Strategic considerations, political calculations, hidden agendas that don't make it into press releases. Let's dig into that possibility next. V1-4, Part 8, Hidden Goals and Strategic Posturing. Vaughan. Science doesn't happen in a vacuum. It happens in a world of budgets, politics, international competition, and institutional prestige. When the European Space Agency decides to redirect instruments aboard a €1 billion flagship mission, that decision isn't purely about spectra and coma dynamics. It's also about visibility, reputation, and positioning on the global stage. Consider the optics. ESA announces that JUICE, Europe's ambitious mission to Jupiter, will observe an interstellar comet during a critical window when Earth-based telescopes are blind. Headlines appear in major publications. Science journalists write articles. Social media buzzes. Suddenly, ESA is at the center of a story that captures public imagination. Interstellar visitors, mysterious comets, spacecraft pivoting to investigate. It's the stuff of space opera. This is valuable. Space agencies compete for funding, public support, and scientific credibility. NASA dominates the conversation with its Mars rovers, Artemis lunar program, and James Webb Space Telescope. China's space program is ascending rapidly, with lunar missions, Mars landers, and plans for a space station. Russia, despite economic challenges, maintains a proud spacefaring legacy. ESA, by comparison, often plays the supporting role, important, respected, but not always the headline act. But here, ESA gets to be the protagonist. They're the ones with a spacecraft positioned to observe 3I Atlas during the blind spot. NASA's Juno is too far away, still at Jupiter. China's missions are focused on the Moon and Mars. Russia's deep space capabilities are limited. ESA has the field to themselves. That's a rare advantage, and they're capitalizing on it. This isn't cynical, it's strategic. Space exploration is expensive. Taxpayers and governments fund it, and they want to see returns, not just scientific papers, but inspiration, achievement, prestige. A successful observation campaign of an interstellar comet, especially one that yields groundbreaking data, justifies past investments and secures future funding. It demonstrates capability, agility, and vision. It shows that ESA can respond to unexpected opportunities, that their missions are worth the cost. There's also a signaling aspect. By greenlighting this observation campaign quickly, within weeks of the Mars orbiter images, ESA sends a message to the international space community. We're nimble. We can make decisions fast. We can pivot our flagship missions to chase targets of opportunity. That's not a given in the world of space agencies, where decision-making often involves layers of committees, review boards, and approval processes. If ESA can demonstrate that they're more agile than their reputation suggests, that helps in negotiations, partnerships, and future mission planning. Behind the scenes, there may have been internal debates, mission scientists arguing for the observations, engineers raising concerns about margins, program managers weighing risks against rewards, decision-makers considering not just science but public relations, political capital, and institutional positioning. In these debates, scientific merit is necessary but not always sufficient. You also need advocates, momentum, and timing. Imagine the pitch. We have a once-in-a-generation opportunity to study an interstellar comet up close, during a window when nobody else can observe it. The science could be transformative, the public will love it, the media will cover it, and if we succeed, we'll have demonstrated that JUICE is one of the most capable and flexible deep space missions ever flown. That's a compelling case, even if the margins are tight and the risks real. There's also the possibility of hidden science goals, objectives that aren't prominently featured in press releases, but are nonetheless important to specialists. For instance, 3I Atlas offers a chance to test theoretical models of interstellar comet composition, structure, and evolution. If those models are wrong, if the comet reveals unexpected isotopic ratios, exotic molecules, or anomalous dust properties that could challenge our understanding of planet formation, stellar evolution, and galactic chemistry. Those are big questions, the kind that drive careers and secure grants. Some researchers might also be interested in testing observational techniques and data pipelines. How well can you track a fast-moving interstellar object with a deep space probe? What challenges arise in real-time navigation, pointing, and data collection? Can you develop autonomous systems that adjust observations based on incoming data? These are lessons that feed into future missions, including ESA's Comet Interceptor, which is designed specifically to intercept a newly discovered comet or interstellar object. In that sense, the 3i Atlas campaign is a live stress test. It's a rehearsal for future encounters, a chance to debug systems, train teams, and refine protocols. If JUICE succeeds, the lessons learned will inform Comet Interceptor's design and operations. If JUICE struggles, those struggles will highlight weaknesses that need addressing. Either way, you gain knowledge that's hard to acquire any other way. There's also the geopolitical dimension. Space is increasingly a domain of strategic competition. Not military necessarily, but in terms of technological prowess, scientific leadership, and international influence. The nation or agency that leads in space exploration gains soft power, the ability to shape narratives, attract partnerships, and set agendas. ESA, as a consortium of European nations, uses space missions to project collective capability. Success in space strengthens European identity and cooperation, especially at a time when political unity faces challenges. Observing 3i Atlas with JUICE is a small piece of this larger puzzle. It won't shift geopolitical balances on its own, but it contributes to a broader narrative. Europe is a serious player in space. Europe can do things nobody else can. Europe's investments in science and technology pay off in tangible, impressive ways. Of course, none of this is publicly stated. ESA's press releases emphasize science, discovery, and the excitement of exploring an interstellar visitor. They don't talk about budgets, competition, or institutional positioning, but those factors are always there, shaping decisions in ways that aren't always visible from the outside. So when you ask, why is ESA doing this? The answer is layered. Yes, the science is compelling. Yes, the opportunity is rare. But also, yes, the visibility is valuable. The prestige is worth something. The demonstration of capability matters, and the potential returns, both scientific and strategic, justify the risks and costs. Which brings us back to the comet itself, because ultimately strategy and politics only matter if the target is worth the attention. And 3i Atlas, it turns out, is strange enough to demand that attention. Let's dive into the anomalies, the mysteries, the puzzles that make this comet genuinely intriguing, and perhaps worthy of the risks ESA is taking. Vuon Set, Part 9, Comet Mysteries, Anomalies and Intriguing Puzzles. Vuon Set, 3i Atlas is not behaving like a typical comet. Oh, it's definitely a comet. Outgassing, coma tail, all the hallmarks are there. But when you dig into the details, when you look at the spectroscopy, the polarimetry, the dust properties, the activity profile, things start to look odd. Not alien odd, just different odd. The kind of different that makes scientists furrow their brows and say, that's not what I expected. Let's start with the carbon dioxide to water ratio. Most comets are water dominated. When they warm up near the sun, water ice sublimates, creating the bulk of the coma. Carbon dioxide is present, usually at levels 10 to 50% of water by molecule count, sometimes less. But 3i Atlas flips that script. James Webb Space Telescope observations show a CO2 to H2O ratio of roughly 8 to 1. 8 carbon dioxide molecules for every 1 water molecule. That's extreme. Why does this matter? Because composition tells you about origin. Comets are fossils, remnants of the protoplanetary disk where they formed billions of years ago. The mix of ices, water, carbon dioxide, carbon monoxide, methane, ammonia reflects the temperature and chemistry of that environment. Water freezes out at relatively warm temperatures, around 150 Kelvin. Carbon dioxide freezes at lower temperatures, around 60 to 70 Kelvin. If a comet is CO2 rich, it likely formed in a colder region, farther from its parent star where carbon dioxide could condense as readily as water. 3i Atlas, then, might be telling us that it formed in the outer reaches of another star's protoplanetary disk, or perhaps in a region where carbon was more abundant relative to oxygen, shifting the chemistry, or perhaps in a molecular cloud that collapsed into a star system, carrying pre-solar material with unusual isotopic and chemical signatures. This is exciting because it's a direct sample of another star. Systems building blocks. Solar system comets teach us about our own history. Interstellar comets teach us about galactic diversity. Each one is a messenger from a distant stellar neighborhood, carrying clues about conditions we can't easily observe any other way. But the CO2 ratio isn't the only oddity. Ground-based telescopes detected water ice, actual ice particles, not just vapour, in the coma at relatively large distances from the nucleus. Normally, water ice sublimates quickly under sunlight. You expect vapour, not solid ice, except very close to the nucleus where particles have just been ejected. But 3i Atlas shows icy grains surviving longer, travelling farther. This suggests either the ice is protected somehow, coated with organics, mixed with darker dust, or the particles are larger than typical, giving them more thermal inertia. Then there's the colour. Optical spectroscopy reveals a red slope, meaning the comet reflects more red light than blue. This is characteristic of certain asteroids, D-type specifically, which are thought to be primitive organic-rich objects. The redness likely comes from complex carbon compounds, tholins, which form when simpler molecules are irradiated over long periods. Seeing this in an interstellar comet suggests that similar processes occur in other stellar systems. But it also raises questions about the comet's history. Has it been floating through interstellar space for millions of years, slowly accumulating cosmic ray damage? Or did it form with these organics already present? Ultraviolet observations add another layer. Hydroxyl emission, OH, a fragment of water molecules, was detected when the comet was beyond 3 astronomical units from the Sun. That's far out, where sunlight is weak and temperatures are low, yet the comet was already active, shedding water. This suggests either a very volatile-rich surface, possibly loaded with supervolatiles like carbon monoxide or nitrogen, that can drive activity even at large distances, or some internal heat source. Maybe radioactive decay of embedded isotopes, though that's speculative, and then there's the polarimetry. This is where things get truly weird. When light scatters off particles, it becomes partially polarized. The electric field oscillates preferentially in certain directions. The degree and direction of polarization depend on particle size, shape, and composition. By measuring how polarized the scattered light is at different angles, you can infer properties of the scattering particles. 3i Atlas shows extreme negative polarization at small phase angles, the angle between the Sun, the comet, and the observer. Around 7 degrees phase angle, polarization reaches negative 2.7%. The inversion angle, where polarization switches from negative to positive, is around 17 degrees. This curve shape is unlike any solar system comet. It's also unlike most asteroids. It's unique. What does this mean? Likely that the dust particles are very small, possibly fluffy aggregates, possibly with complex internal structure. Maybe they're coated with organics that change how light interacts with them. Maybe they're composed of exotic silicates or carbonaceous material that doesn't exist in solar system comets. Or maybe the scattering is dominated by gas and tiny nanoparticles rather than larger dust grains. The size of the nucleus is also uncertain. Estimates range from as small as 320 meters to as large as 5.6 kilometers in diameter. That's a huge range. The uncertainty comes from the fact that we can't resolve the nucleus directly. It's hidden in the coma's glow. You estimate size by measuring brightness and making assumptions about reflectivity, or albedo. If the nucleus is dark, low albedo, it must be larger to produce the observed brightness. If it's bright, high albedo, it can be smaller. Without knowing the albedo, you can't pin down the size. This matters because size affects everything. A small nucleus has different thermal properties, different structural strength, different likelihood of fragmentation. A large nucleus carries more mass, more volatiles, more potential for sustained activity. Not knowing which you're dealing with introduces significant uncertainty into models. Putting all this together, high CO2, icy grains, red colour, early activity, bizarre polarization, uncertain size, you get a picture of a comet that doesn't fit neatly into our taxonomies. It's not like solar system comets. It's not quite like 2I/Borisov, the previous interstellar comet, which was more normal in many respects. 3i Atlas is an outlier. Does this make it dangerous? No. Anomalous doesn't mean threatening. It just means interesting, scientifically valuable, worthy of attention. Does it make it potentially revolutionary? Maybe. If the JUICE observations confirm some of these anomalies and add new details, unexpected molecules, isotopic ratios that challenge formation models, dust structures that don't match any known material, it could force us to rethink how comets form, how planetary systems evolve, how material moves through the galaxy, or it could turn out that 3i Atlas, despite its quirks, still fits within the broad envelope of natural cometary behaviour, that the anomalies are real but explicable, interesting but not paradigm-shifting. We won't know until the data comes in. And that's the tension. That's why ESA is watching so closely, because this comet, more than most, has the potential to surprise us, and surprises in science are where breakthroughs happen. But surprises can also be problems, things that don't go according to plan, risks that materialise, failures that cascade. So before we get too carried away with excitement, let's talk about what could go wrong. Josnund, Part 10, Risk Scenarios, Failure Modes and Surprise Discoveries. Jamwianyand. Space missions operate on the edge of disaster. That's not hyperbole. It's the reality of sending complex machines into hostile environments where repair is impossible and mistakes are unforgiving. JUICE, like all deep space probes, has multiple failure modes built into its design, not because engineers expect failure, but because they plan for it. Redundant systems, safe modes, contingency protocols. But every mission also has vulnerabilities, points where things can go wrong in ways that overwhelm the safeguards. Let's start with fragmentation. Comets are fragile. They're not solid rock. They're loosely bound mixtures of ice, dust and organics, held together by weak cohesion and occasional structural ice frameworks. Under thermal stress, rapid heating from the sun, internal pressure from sublimating volatiles, comets can crack. Sometimes they split into multiple pieces. Sometimes they disintegrate entirely, spreading debris along their orbital path. 3i Atlas, approaching perihelion, is under maximum thermal stress right now. If it fragments during the observation window, several things could happen. Best case, it breaks into a few large pieces, each individually trackable. JUICE adjusts, pointing to follow the brightest fragment, continues observations. Science teams get excited because fragmentation events reveal internal structure. You see layers, composition gradients, maybe even pockets of different ices. Worst case, it shatters into a cloud of small debris. The coma becomes chaotic, harder to interpret. Dust production spikes, overwhelming sensors. Navigation uncertainty increases because you're no longer tracking a single well-defined nucleus. JUICE might struggle to maintain accurate pointing if the comet's centre of mass shifts, or if multiple fragments create confusion about where to aim. There's also a slim chance, very slim, that a fragment travels on a trajectory that brings it closer to JUICE than expected. Space is big, the odds are minuscule, but if you're tracking a comet and a piece unexpectedly heads your direction, that's a problem. JUICE has no ability to dodge. It can't perform rapid collision avoidance maneuvers. If debris intersects its path, it's just bad luck. More likely are instrument-level failures. Pointing instruments sunward in the inner solar system risks stray light contamination. Even with baffles and shields, sunlight can scatter off surfaces, enter optical paths, saturate sensors. If a camera or spectrometer gets overwhelmed by stray light, it returns useless data, images that are washed out, spectra dominated by noise. Mission teams can try to mitigate this by adjusting pointing angles, using shorter exposure times, or filtering data in post-processing. But if the contamination is severe, you lose observing time. Thermal issues are another risk. If an instrument overheats, onboard systems should shut it down automatically to prevent damage. The spacecraft enters a protective safe mode, stops science operations, and waits for commands from Earth. This is a built-in safety feature, but it's also a loss of observing time. Every hour spent in safe mode is an hour not collecting data. And Earth is light minutes away, at JUICE's distance during November, about 5 to 15 light minutes depending on its exact position. That's a 10 to 30 minute round-trip communication time. If something goes wrong, ground controllers don't find out immediately, and their commands don't arrive instantly. You lose time to latency. Reaction wheel saturation is a subtler problem. As JUICE tracks the comet, adjusting its attitude to follow the comet's motion, reaction wheels accumulate momentum. Eventually they saturate, spinning at maximum speed, unable to provide more torque. At that point, the spacecraft must desaturate by firing thrusters to dump the excess angular momentum. This uses fuel. If the observation campaign requires more frequent desaturation than planned, fuel consumption increases, eating into margins faster than expected. There's also data corruption. Cosmic rays, high-energy particles zipping through space, can strike electronics, flipping bits in memory or causing transient errors in processors. Deep space spacecraft are designed to handle this with error-checking codes, redundant systems, and shielding. But if you're collecting a lot of data rapidly, storing it on board, and downlinking it later, there's a chance some of it gets corrupted. If critical calibration data or key spectra are lost, that degrades the overall science return. Communication link failures are another worry. JUICE's high-gain antenna must point toward Earth to transmit data. If pointing errors occur, navigation uncertainty, software glitches, mechanical issues, the antenna might miss Earth, and the downlink fails. Ground controllers don't receive expected data. They send commands to re-establish the link, but that takes time. Meanwhile, the observation window is ticking away. Now counterbalance all of this with the upside. What if everything works? What if JUICE's instruments perform flawlessly, capturing high-resolution images, detailed spectra, precise particle measurements? What could those data reveal? Exotic molecules for one, complex organics that don't exist in solar system comets, nitriles, amino acid precursors, polycyclic aromatic hydrocarbons. These are the building blocks of biochemistry. Finding them in an interstellar comet suggests that the raw materials for life are common throughout the galaxy, not just in our corner of it. Isotopic anomalies for another. The ratios of isotopes, different versions of the same element with different numbers of neutrons, carry information about the environment where they formed. Solar system comets have characteristic isotopic signatures inherited from the solar nebula. Interstellar comets might have different signatures, reflecting different stellar environments, different supernovae contributions, different galactic chemical evolution. If 3I Atlas shows deuterium to hydrogen, ratios or nitrogen isotope ratios that differ significantly from solar system norms, that's a major discovery. Dust structure could also surprise us. If JUICE's instruments can analyze scattered light from dust particles in detail, they might reveal particle shapes, aggregation states, or compositions that don't match any known solar system analogues. This would challenge our models of dust formation in protoplanetary disks and force us to rethink how planets coalesce from smaller particles. There's also the possibility of detecting interactions between the comet and the interstellar medium. 3I Atlas is exiting the solar system on a hyperbolic trajectory, heading back into interstellar space. As it moves outward, it will eventually re-enter the interstellar medium, the dilute gas and magnetic fields that fill the space between stars. The transition might produce observable effects, changes in coma behavior, shock waves, particle acceleration. If JUICE can catch hints of this transition, it would be the first observation of a comet re-entering interstellar space, a unique dataset. Even partial success would be valuable. Suppose thermal constraints limit observation time, or stray light degrades some data, or communication issues cause delays. You still end up with the best spacecraft-based dataset of an interstellar comet to date. You still learn something. Maybe not everything you hoped for, but something. And in science, incremental progress is often as important as breakthroughs. The question is, will the gamble pay off? Will JUICE return data that justifies the risks, the fuel expenditure, the margin erosion? Or will this be remembered as a bold attempt that didn't quite deliver? We won't know until late November, when the observation window closes and data starts flowing back to Earth. Until then, we're in suspense. The spacecraft is out there, alone, executing commands uploaded weeks ago, tracking a comet that nobody on Earth can see. It's a moment of blind faith, trusting that the calculations were correct, the risks were acceptable, and the potential rewards were worth pursuing. But 3I Atlas isn't just a story about one comet and one spacecraft. It's part of something larger, something that's been unfolding across the galaxy for billions of years. To understand why this comet matters, we need to zoom out. We need to look at the cosmic context, the forces that shape our galaxy, and the mechanisms that might send objects like 3I Atlas careening through interstellar space in the first place. Because recent discoveries suggest our galaxy is far more dynamic, far more violent than we once thought. And that dynamism might be the key to understanding where interstellar comets come from. The One Must, Part 11, Gaia's Great Wave and Galactic Ripples, Implications for Comet Origins. The Milky Way looks calm in photographs, A serene spiral of stars, dust lanes tracing elegant arms, everything seemingly frozen in cosmic stasis. But that's an illusion. Our galaxy is a dynamic churning system where gravitational forces constantly reshape structure, where stars don't simply orbit smoothly, but get pushed, pulled, and perturbed by interactions we're only beginning to understand. Recently, astronomers using data from the Gaia spacecraft, Europe's astrometry mission, mapping the positions and motions of billions of stars, discovered something extraordinary. They found a wave. Not a wave of water or sound, but a wave of stellar density rippling through the galactic disk. Thousands of stars displaced from their expected positions, moving in coordinated patterns that suggest a massive perturbation passed through the Milky Way's disk relatively recently in galactic terms. They're calling it the Great Wave, though it's not a single crest but rather a complex pattern of oscillations. Imagine dropping a stone into a pond. Ripples spread outward, expanding, interfering with each other, creating patterns. Now imagine that on a galactic scale. Some event, perhaps the passage of a satellite galaxy, perhaps the gravitational influence of the Milky Way's central bar structure, perhaps something we haven't identified yet, sent a shockwave through the disk. Stars were jostled, their orbits shifted, and now, millions of years later, we can see the evidence in their current positions and velocities. What does this have to do with 3i Atlas? Potentially everything. Because if stars can be perturbed by galactic waves, so can smaller objects. Comets, asteroids, planetesimals, anything in the outer reaches of a star system where gravitational binding is weak. When a wave passes through, it doesn't just affect stars, it affects everything. Picture a comet in the outer Oort cloud of a distant star system, orbiting lazily in the cold dark, thousands of astronomical units from its parent star. Its orbit is barely bound, held by the weakest gravitational threads. Then a galactic density wave passes through. The local gravitational field shifts slightly. That tiny perturbation, acting over millions of years, nudges the comet. Its orbit becomes unbound. It drifts away from its star into interstellar space. Billions of years later, it happens to pass near our Sun. We see it as an interstellar visitor and wonder where it came from. This mechanism, galactic perturbations ejecting objects from star systems, has been theorized before. Close encounters between stars, passage through dense molecular clouds, tidal forces from the galactic core. But the Great Wave adds a new dimension. It suggests that ejections might not be random, they might correlate with galactic structure, with regions where density waves are strong, with times when the galaxy is particularly active. If that's true, then interstellar objects like 3i Atlas might be more common than we thought. Not rare freaks of orbital mechanics, but a natural consequence of galactic dynamics. Every star system sheds comets and asteroids into interstellar space, especially systems in regions where galactic waves are frequent. Over billions of years, the galaxy fills with a population of wanderers, drifting between stars, occasionally falling into other systems. This changes how we think about interstellar space. It's not empty. It's filled with debris, a kind of galactic ocean populated by icebergs and rocks, all moving on their own trajectories, all carrying information about their origins. Every interstellar object we detect is a sample from that ocean, a piece of someone else's star system, delivered to our doorstep by galactic currents we're only beginning to map. 3i Atlas, in this context, might not be special because it's unusual. It might be special because it's typical, a representative sample of what's out there, floating in the space between stars. Its high CO2 ratio, its red colour, its weird polarization, these might be common features of interstellar comets, reflecting the diversity of environments where they formed. Or perhaps 3i Atlas is unusual even among interstellar objects. Perhaps it came from a star system with particularly extreme chemistry. Or perhaps it was ejected during a particularly violent event, a close stellar encounter, a planetary system instability, a supernova shockwave from a nearby explosion. Without more data, we can only speculate. But the connection to galactic dynamics is profound. It means that studying interstellar comets isn't just about comets. It's about understanding how galaxies work, how matter moves through the interstellar medium, how star systems interact with their galactic environment. It's about connecting the smallest scales, individual icy bodies a few kilometers across, to the larger scales, galactic structures hundreds of thousands of light years wide. And it reminds us that our solar system is not isolated. We're embedded in a galaxy that's alive with motion, with forces acting over timescales we can barely comprehend. The objects that visit us from interstellar space are messengers from that larger context. They tell us that the galaxy is more interconnected than we realized, that material cycles between stars, that what happens in one star system can eventually affect another, given enough time. This is why ESA's observation of 3I Atlas matters beyond the immediate science return. It's part of a larger effort to understand our place in the galaxy, to map the flows of matter and energy that shape the cosmic landscape we inhabit. Every data point, every spectrum, every image adds to that map. But galactic waves and interstellar comets aren't the only surprises the universe has delivered recently. Even in our own solar system, in our own neighbourhood, there are discoveries that challenge what we thought we knew. Small bodies hiding in plain sight, waiting to be found. Let's talk about one of those discoveries and what it teaches us about the limits of our knowledge. Japatiangiu, Part 12. New Moon. Orbiting Uranus, tiny bodies, big insights. Wonderund. In early 2025, astronomers announced the discovery of a new moon orbiting Uranus. They've designated it S/2025 U1, pending confirmation and official naming. It's tiny, probably only a few kilometers across, and it orbits near Uranus's ring system, a region cluttered with dust, ice particles, and other small moons. Its discovery came from careful analysis of archival images from ground-based telescopes and possibly from Hubble Space Telescope observations, stacking frames and tracking faint moving objects against the background of stars and Uranus's glow. You might think, so what? Another moon? Uranus has dozens of known moons already. What's one more? But think about the implications. Uranus is a giant planet in our solar system. It's been observed for centuries. Voyager 2 flew by in 1986, capturing detailed images. Hubble has watched it for decades. Ground telescopes monitor it regularly. And yet, we just found a new moon, in 2025, in our own solar system. A moon that was there all along, hidden in the glare and clutter, waiting for someone to look carefully enough. If we can miss a moon of Uranus, a planet less than 3 billion kilometers away, in a system we've studied intensively, what are we missing elsewhere? What other small bodies lurk in the outer solar system, too faint or too distant for our surveys to detect? What objects hide in the asteroid belt, in the Kuiper belt, in the Oort cloud? The answer is probably millions. Our catalogues of small solar system bodies are incomplete. We've found the big ones, the bright ones, the ones that happen to pass close enough to Earth to be easily detected. But for every asteroid we know, there are probably dozens we don't. For every trans-Neptunian object in our catalogues, there are likely hundreds undiscovered. This is the observational bias problem. We can only see what our instruments are sensitive to. Faint objects, distant objects, objects with low albedos, objects in orbits that keep them far from Earth. These escape detection. And the smaller you go, the worse the problem gets. Below a certain size, the solar system becomes statistically unknown territory. This matters for understanding the solar system's structure and history. Small bodies are fossils. They're remnants from the solar system's formation, largely unmodified by geological processes, carrying information about the protoplanetary disk, the migration of giant planets, the bombardment history of the inner system. Every new discovery refines our models, fills in gaps, sometimes overturns assumptions. It also matters for hazard assessment. Small asteroids, if they hit Earth, can cause significant damage. The Chelyabinsk meteor in 2013 was only about 20 meters across, and it exploded with the force of hundreds of kilotons, injuring over 1,000 people. We never saw it coming because it approached, from the direction of the sun, hidden in the glare. If a moon of Uranus can hide in plain sight, so can Earth-crossing asteroids. But the deeper lesson is epistemological. It's about the limits of knowledge. We live in an era of unprecedented astronomical discovery. Surveys like the Sloan Digital Sky Survey, Pan-STARRS, and the upcoming Vera Rubin Observatory are mapping the sky with extraordinary completeness. We're finding exoplanets by the thousands, black holes by the hundreds, distant galaxies by the millions. We have this sense that we've surveyed the universe, that we know what's out there, and then we find a new moon of Uranus, and we're reminded We don't know. Not really. Not completely. We know what we've looked for. We know what our instruments can detect. But there's always something we've missed. Something just below the detection threshold. Something in a blind spot we didn't realize we had. Apply that lesson to 3i Atlas. We've detected 3 interstellar objects now. 3. That's not a census. That's not even a statistically meaningful sample. It's a first glimpse. We're seeing the tip of an iceberg, the brightest, closest, most easily detected examples of a population that's probably vast. For every interstellar comet we find, how many pass through undetected? How many are too faint, too far from the ecliptic plane, too small to trigger our alert systems? Some estimates suggest that at any given time, there might be dozens of interstellar objects within the orbit of Neptune. Most are small, inactive, dark. They pass through silently, unseen, contributing nothing to our knowledge because we never notice them. Only the occasional active comet bright enough to stand out gets detected. This means our understanding of interstellar objects is skewed. We're seeing a biased sample, the loud ones, the gassy ones, the ones that conveniently announce their presence by outgassing and creating comas. The dark, inert objects, which might actually be more common, remain invisible. It's like trying to understand bird migration by only watching the ones that sing loudly. You miss the silent majority. The discovery of a new Uranian moon underscores this. It reminds us that even close to home, even in well-studied regions, there are surprises. And if that's true for our solar system, it's doubly true for the galaxy. Every survey has limits. Every catalogue is incomplete. Every model is provisional. This is why infrastructure matters. Why upgrades to telescopes, antennas, data processing systems make a difference. Because the better your tools, the more you see. The more you see, the better your understanding. Let's talk about one such upgrade that's enabling missions like JUICE to push boundaries. JUICE Spills. Part 13, the Deep Space Antenna Upgrade, Why It Matters for this mission. JUICE Spills. In the Australian outback near the town of New Norcia sits a 35-metre radio antenna. It's part of the European Space Agency's Deep Space Ground Station Network, a system of antennas scattered around the globe that communicate with ESA's missions in the far reaches of the solar system. Recently, this antenna underwent significant upgrades, improved receivers, higher power transmitters, better signal processing systems. The goal: increase data throughput, reduce latency, support more complex missions. Timing is interesting. The upgrade was completed roughly coincident with JUICE's cruise phase, right when the spacecraft is executing complex maneuvers and preparing for its observation campaigns, including the 3i Atlas observations. Is this a coincidence? Probably, in the sense that the upgrade was planned years ago, long before anyone knew about 3i Atlas. But it's a fortunate coincidence, because the improved antenna capabilities enable exactly the kind of intensive data collection and rapid command turnaround that this observation campaign requires. Here's why antenna capability matters. When JUICE observes 3i Atlas, it collects data, images, spectra, particle counts. That data is stored on board in solid-state memory. Later, the spacecraft slews to point its high-gain antenna toward Earth and begins transmitting. The data travels through space at the speed of light. Taking minutes to arrive, ground stations receive the signal, amplify it, decode it, and forward it to mission control. The amount of data you can transmit per unit time, the data rate, depends on several factors: transmitted power, antenna gain, distance, receiver sensitivity, and interference. The farther the spacecraft, the weaker the signal. The weaker the signal, the lower the data rate, or the longer it takes to send a given amount of data. A better ground antenna improves receiver sensitivity. It can detect weaker signals, which means the spacecraft doesn't have to transmit at maximum power, saving energy and reducing thermal stress on transmitters. Or it means you can achieve higher data rates at the same power, getting more data back per pass. Or it means you have more margin. If the signal is slightly weaker than expected due to pointing error, interference, or spacecraft issues, the antenna can still lock on and receive data. For the 3i Atlas campaign, this matters because the observation window is limited, 3 weeks. During that time, JUICE needs to collect as much data as possible and downlink it efficiently. If communication passes are productive, high data rates, minimal errors, you maximize science return. If they're problematic, low data rates, corrupted data, lost locks, you waste time and possibly lose data when onboard storage fills up. The new Nausea antenna, with its upgrades, provides ESA with robust communication capability during this critical window. It's like having a high-speed internet connection instead of dial-up. The faster you can download data, the more room you free up on board for new observations, the less time you spend in downlink mode, the more time you can spend observing. There's also redundancy. ESA has multiple ground stations, New Nausea in Australia, Cebreros in Spain, Malagu in Argentina. If one has issues, weather, equipment failure, scheduling conflicts, others can cover. But having one recently upgraded station in an optimal longitude for certain JUICE communication windows reduces pressure on the network. This kind of infrastructure investment doesn't make headlines. It's not sexy. A new Mars rover gets attention. A flashy mission to an asteroid captures imaginations. But unglamorous ground systems, antennas, data centers, tracking networks are the backbone that makes everything else possible. Without them, spacecraft are deaf and mute. With them, spacecraft become extensions of human presence, reaching into the far corners of the solar system and beyond. The timing suggests that ESA anticipated needing robust deep space communication for missions like JUICE. The fact that this capability is available now, during the 3i Atlas window, is enabling science that might otherwise be marginal or impossible. It's an example of how mission success depends not just on the spacecraft but on the entire ground infrastructure supporting it. And as we look toward the future, toward more ambitious missions, toward encounters with more interstellar objects, this infrastructure will become even more critical. Because the next time an interstellar visitor appears, and there will be a next time, we'll need to respond quickly, communicate reliably, and process data efficiently. Let's talk about what that future might look like, and how the lessons from 3i Atlas will shape it. Sopan Part 14. Future Missions, Preparedness and Interstellar Readiness. The European Space Agency has a mission on the books called Comet Interceptor. It's not launched yet, current target is sometime in the late 2020s, but its concept is revolutionary. Instead of designing a mission to visit a specific comet known in advance, Comet Interceptor will be parked at the Sun-Earth L2 Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth, and it will wait. Wait for what? For a newly discovered comet. Preferably a long-period comet making its first visit to the inner solar system, a pristine object that's never been heated by the sun before. Or better yet, an interstellar object. Something like 3i Atlas, but detected earlier, with more warning. When a suitable target is found, Comet Interceptor will leave L2 and execute a trajectory to intercept the comet, arriving at a predetermined distance and releasing sub-probes to fly through the coma, taking measurements from multiple angles simultaneously. It's an intercept mission by design, built from the ground up for flexibility and rapid response. This is the future of interstellar object exploration. Not missions designed for specific targets known decades in advance, but missions designed for targets we haven't found yet. Missions that sit on standby, ready to deploy when opportunity knocks. JUICE's observation of 3i Atlas serves as a dress rehearsal for this future. It's testing concepts. How quickly can you retarget instruments? How do you navigate to an unpredictable target? How do you balance primary mission objectives with opportunistic science? What are the operational challenges of tracking a fast-moving object with limited Earth-based support? The lessons learned will feed into Comet Interceptor's design and operations. If JUICE encounters problems, thermal overheating, pointing errors, communication bottlenecks, those problems inform what Comet Interceptor needs to avoid. If JUICE succeeds smoothly, that success validates certain operational approaches and gives confidence that similar strategies will work in the future. But Comet Interceptor is just one mission. The broader question is, how do we prepare for a future where interstellar objects are regular visitors, not rare anomalies? Because as our detection capabilities improve, better telescopes, wider surveys, automated alert systems, we're going to find more. Maybe not every year, but regularly. Maybe one every few years, maybe more. When that happens, we need to be ready. Ready to observe, ready to analyze, ready to respond. This requires several things. First, detection networks. We need all sky surveys that can spot faint moving objects quickly. The Vera Rubin Observatory, when it comes fully online, will survey the entire visible sky every few nights, detecting transient events, moving objects, anything that changes. It will find interstellar objects earlier, giving more time to plan observations. Second, rapid response protocols. Alerts need to flow quickly from observatories to mission operation centers. Decisions about whether to retarget spacecraft need to happen in days or weeks, not months. This requires streamlined approval processes, pre-authorized contingency plans, and teams trained to act fast. Third, flexible spacecraft design. Future missions should include modular sensor packages, standardized interfaces, and sufficient delta-V margins to handle unexpected targets. Maybe small CubeSats that can be released from larger spacecraft. Essentially disposable probes designed to be sacrificed for close flybys of high-value targets. Fourth, data infrastructure. High bandwidth communication, robust ground stations, rapid data processing pipelines. When an interstellar object passes through, you might only have weeks to collect data. You can't afford bottlenecks in getting that data back to Earth and into scientists' hands. Fifth, international coordination. Space exploration is increasingly collaborative. NASA, ESA, JAXA, CNSA, other agencies, they all have assets that could contribute to observing interstellar objects. Sharing data, coordinating observations, avoiding duplication of effort. This requires agreements, frameworks, and trust built over years of cooperation. Sixth, public engagement. Interstellar objects capture imaginations. They're tangible evidence that we're part of a larger galaxy, that material flows between star systems, that we're connected to the cosmos in ways we're only beginning to understand. Communicating this to the public, building support for missions, inspiring the next generation of scientists and engineers, that's essential for sustaining long-term exploration efforts. 3i Atlas is a test case for all of this. It's showing us what works, what doesn't, and what we need to improve. JUICE wasn't designed as an interstellar object interceptor, but it's being used as one anyway, improvised, adapted on the fly. The next mission won't need to improvise, it will be built for this from the start, and that's exciting, because the galaxy is full of objects like 3i Atlas, comets, asteroids, planetesimals, all drifting between stars, carrying information about distant worlds. Everyone we detect is a gift, a free sample delivered to our doorstep. The better we get at studying them, the more we learn about the diversity of planetary systems, the commonality of materials, the mechanisms that govern how matter moves through the galaxy. We're entering an era where interstellar visitors are no longer once-in-a-lifetime events, but regular occurrences. An era where we have spacecraft positioned to study them, ground networks ready to track them, and scientific communities eager to analyze them. 3i Atlas is part of that transition, a moment when we shifted from passive observers to active participants in the study of interstellar space. But what does it all mean? Why does any of this matter? Let's step back, take a breath, and reflect on the bigger picture. Where does 3i Atlas fit in the grand story of human exploration, scientific discovery, and our evolving relationship with the cosmos? Check the world. Part 15. Closing reflections and big questions. Control. So here we are, at the end of this investigation. We started with a simple question. Did the European Space Agency redirect JUICE to intercept an interstellar comet? And the answer, as it turns out, is both yes and no. No, in the sense that JUICE's trajectory remains unchanged. The spacecraft is still on course for Jupiter. Its orbit wasn't altered. No significant delta-V was expended chasing 3i Atlas. The term intercept is misleading if you interpret it as a physical flyby. Yes, in the sense that ESA redirected attention, resources, and operational focus. They committed a flagship missions instruments to a 3-week observation campaign during a critical window. They pushed boundaries, thermal, pointing, data, fuel margins, to seize an opportunity that won't come again. In every way that matters operationally, they pivoted. Was this risky? Yes. Was it justified? That depends on the data. If JUICE returns spectra showing exotic molecules, images revealing unexpected coma structures, particle measurements, detecting anomalous interactions, then the gamble pays off. ESA will have captured a dataset that transforms our understanding of interstellar comets, validates their responsiveness, and demonstrates the value of flexible mission planning. If the data is marginal, compromised by thermal issues, limited by stray light, incomplete due to communication problems, then the decision will look more questionable. Not necessarily wrong, but expensive. A diversion that consumed resources for modest returns. We won't know until the data is analysed, published, peer-reviewed. That takes months, sometimes years. But the immediate returns, the images, the headlines, the public engagement, have already happened. ESA got the visibility boost, they demonstrated capability, they captured imaginations. And 3i Atlas? It remains an enigma. A comet with too much carbon dioxide, dust that scatters light strangely, colours that don't quite fit, activity at unexpected distances. Is it genuinely anomalous, or just at the edge of the bell curve of cometary diversity? JUICE's observations might answer that, or they might just raise more questions. Either way, 3i Atlas has already taught us something important. Interstellar objects are not all alike. 1i/Oumuamua was weird, elongated, tumbling, non-outgassing. 2i/Borisov was relatively normal, a standard comet, just from another star. 3i Atlas is somewhere in between, clearly a comet but with odd properties. This diversity tells us that planetary systems across the galaxy produce a wide range of objects, that formation conditions vary, that no single model captures everything. It also tells us that we need more data. 3 objects is not enough to draw conclusions. We need dozens, hundreds, eventually thousands. We need to characterize the population, understand the distributions, identify patterns and outliers. Only then can we start to make confident statements about what's typical and what's extraordinary. This is the long game of science. Individual observations matter, but it's the accumulation over time that builds understanding. 3i Atlas is one data point. Important, valuable, but still just one. The real payoff comes when we can compare it to the next interstellar visitor, and the one after that, building a catalogue, refining models, testing theories. And that brings us to the existential question lurking beneath all of this. What does it mean to study objects from other star systems? We're not just doing astronomy anymore, we're sampling the galaxy. We're reaching beyond our solar neighbourhood, gathering information about places we'll never visit, stars we'll never orbit. We're connecting to the larger cosmos in a direct, tangible way. Every interstellar comet is a messenger. It carries ice formed in another stellar nebula, dust grain shaped by another star's radiation, molecules synthesized in conditions different from anything we experience when we analyze that. We analyze material. We're touching another world. When we measure its composition, we're learning about chemistry that happened light years away and billions of years ago. This is profound. It's easy to get lost in the technical details, delta V budgets, thermal margins, spectrographic analysis, and forget the bigger picture. But step back and consider, we are living in a time when humanity routinely detects and studies objects from beyond our solar system. That was science fiction a generation ago. Now it's just science, and it's accelerating. The detection rate will increase, our response capabilities will improve, future missions like Comet Interceptor will be ready, ground telescopes will become more sensitive, alert networks will become more sophisticated. Each interstellar object we detect will be studied more thoroughly than the last. In a decade, we might have dozens of well-characterized interstellar objects in our catalogues. In a century, maybe thousands. We'll map the distribution of compositions, identify trends, correlate properties with galactic structure. We'll start to understand how material cycles through the galaxy, how star systems exchange debris, how the interstellar medium connects distant worlds, and maybe, just maybe, one of those objects will surprise us. Not in the way internet conspiracy theorists hope, not an alien probe or engineered artifact, but something genuinely unexpected. A comet with impossible isotopic ratios, an asteroid made of a mineral that doesn't exist in the solar system, a signature that challenges our models of stellar evolution or galactic chemistry. Science advances through anomalies. When observations don't match predictions, that's when things get interesting. 3i Atlas, with its weird polarization and high CO2, might be one of those anomalies. Or it might be explicable, fitting into expanded models once we understand it better. Either way, the process matters. The willingness to look, to investigate, to push boundaries. ESA's decision to commit JUICE to observing 3i Atlas embodies that willingness. It's a statement. This is worth our time, our resources, our attention. We don't know what we'll find, but we're going to look anyway. That's the spirit of exploration. Not certainty, but curiosity. Not knowing the outcome, but accepting the risk. Not waiting for perfect conditions, but seizing opportunities when they arise. And as we look forward to the next interstellar visitor, to Comet Interceptor's launch, to improved surveys and better missions, we can ask ourselves, are we ready? Ready not just technologically, but philosophically? Ready to encounter the unexpected, to revise our models, to accept that the galaxy is stranger and more diverse than our theories predict? 3i Atlas is a test, not just of JUICE's instruments or ESA's operations, but of our readiness to engage with the galaxy as active participants rather than passive observers. We're no longer just looking at stars through telescopes. We're intercepting their debris, analysing their remnants, learning their secrets. If in 5 years another interstellar object appears, brighter, closer, more accessible, what will we do differently? Will we have Comet Interceptor on station ready to deploy? Will we have better coordination between agencies? Will we have learned from JUICE's experience, avoided its pitfalls, built on its successes? The answers depend on choices we make now. On investments in infrastructure, on mission designs that prioritise flexibility, on international agreements that enable rapid response, on public support that sustains funding through budget cycles and political changes. 3i Atlas is more than a comet. It's a catalyst. It's forcing us to think about how we explore, how we prepare, how we respond to a galaxy that's more accessible than we ever imagined. Because the objects are out there, right now, drifting through the space between stars. Some will pass near our sun, some will detect, some will study, and each one will teach us something new about our place in this vast, dynamic, interconnected galaxy we call home. The question isn't whether we'll encounter more interstellar visitors. The question is, what will we learn when we do, and will we be ready to listen? The observation window closes on November 25th, 2025. Soon we'll know what JUICE saw. Soon we'll have data, and then the real work begins, analysing, interpreting, publishing, debating. Science moves slowly, methodically, carefully, but it moves, and somewhere out there, beyond Neptune, beyond the Kuiper Belt, beyond the heliopause, another interstellar object is making its way toward our sun. We haven't detected it yet. We don't know its trajectory, its composition, its story, but it's coming, and when it arrives, we'll be watching.